I thought I'd introduce this topic with a quick example, a very small example. So this is just a four-letter word. But what we're looking at is permutations of things where the things that we're permuting may have repeats. You may have indistinguishable things. So the word geek here has four letters, but two of them, these two E's, you can't tell them apart, right? So, I mean, four things, the permutations of four things is 24. I feel like it should be related to that. And if I could tell them apart, and on the back sides of these I have put little subscripts on them so I can tell the letters apart. Of course, the ones on the G and the K don't matter, but the E1, E2 serve to distinguish the E's from one another. Now, of these things, there's definitely 24 permutations of them. What if I erase the subscripts, right? Come back to this setting. How would you know whether they were in that order or this order? In other words, you've got a double count of every single permutation. You might do this, say, okay, 4 factorial, there's 24 of them. But because we can't tell which order the two E's showed up in, we've overcounted by a factor of 2. Well, we divide by 2 factorial. And if there were 3 E's, I would be dividing by 6 by the possible reorderings of the E's. Awesome. The general formula there is you'll have n factorial for the number of symbols, and then you'll divide out by the factorials of any repeated symbols that appear. We'll do an extended example that's a little bit bigger and more interesting next. Let's apply that thinking to this sort of classic question, which is how many ways can you rearrange the letters of Mississippi? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters here. 11 letters all told. But there's a single M, one M. There's 1, 2, 3, 4 I's. There's 1, 2, 3, 4 S's. And finally 2 P's. So if you want to count the total number of permutations of this, where you can't tell any of the S's apart and you can't tell any of the I's apart, you start with 11 factorial, but you divide out by the number of permutations that potentially that would be the same if you just changed an order of the S's or changed some ordering in the I's. You could think of this as put some subscripts on all the I's, for instance, and also you would do that on the S's and on the P's. You don't really need one on the M, it's by itself, but now you've got distinguishable things, so 11 factorial is right. Then you ask yourself, well, how does the count change if I erase these subscripts? There are 24, that's 4 factorial, different permutations of the original things that look the same now that I can no longer tell the I's apart. So we would take 11 factorial and we would divide by 4 factorial. That deals with the 4 I's. But we'd also have to divide by 4 factorial to get rid of the dependency on the S's being distinguishable, and finally by 2 factorial to get rid of the issue about switching P1 and P2. And indeed, there's actually also a 1 factorial, but that doesn't change anything. What that does do, though, is give you a nice pattern to look for. The numbers in the bottom all add up to the number that's in the top. 4 and 4 is 8, 9, 10, 11. I don't need the factorials of them, but but the pre-factorialized numbers, 8, 9, 10, 11. And 11 is in the numerator. There's actually a notation for this. This is what's called a multinomial coefficient. Oops. Multinomial coefficient. And the binomial coefficients that we've looked at previously are actually, you can think of them as an example of this. So the solution that we just wrote down, 11 factorial over 4 factorial, 4 factorial, 2 factorial, and 1 factorial, as a multinomial coefficient is written like this. It looks like a binomial coefficient, so there's no fraction bar, but some things in parentheses. The top has the 11 in it, and the other numbers, 4, 4, 2, and 1, go down below. So that's understood to be what we did here, 11 factorial over 4 factorial, 4 factorial. If I wanted to give you what n choose k is in this form, you could do it too. It's n choose k and n minus k. That's sort of a strange way to write the ordinary binomial coefficient, n choose k. Think of it as a multinomial where the multi is 2. There's 2 bits to deal with. All right, so those turn out to be useful in a lot of settings. We're not going to see much more of them, but it is fun to be able to solve these recreational math problems about a number of arrangements of letters. If you want a challenge, try to figure it out for Connecticut. How many different ways could the letters of Connecticut be permuted where we can't tell any of the C's or the T's from one another? I think there's other letters in there that might be repeated. Anyway, you'll have to check. The multinomial coefficient that I just wrote down can also be written as a product of binomial coefficients, and I think this is sort of instructive. We had 11, choose 4, 4, 2, and 1, right? Was that up to 11? Yeah. It's equal to, well, you think about using the multiplication rule to construct a permutation of the letters that we were talking about. Basically, I've got, sort of imagine you have 11 blanks, 11 places to put letters. Well, out of those 11 places, choose 4 of them as a location for the 4 eyes, right? Now, having done that, there'll be 7 positions open, right? So, out of those 7, choose 4 of them to get the, what is this now, the S's. Then there'll be, how many left over after we picked 4 out of our 7? There'll be 3 positions left open. So we'll pick, out of those 3, we'll pick spots to put our P's. And now there's a single spot open. That one position is where we're going to have to put our 1M. So that product is sort of the multiplication rule version of thinking about how to get this. Now, well, let's write it out in terms of the definition of the binomial coefficients. The top of the first one is 11 factorial, and in the bottom we have 4 factorial, and the difference, which is 11 minus 4, 7 factorial. The next one, 7 choose 4, that's got 7 factorial upstairs, 4 factorial downstairs, and the difference between 7 and 4, which is 3 factorial. And 3 choose 2, that's 3 factorial over 2 factorial and 1 factorial. And finally, 1 factorial over 1 factorial and 0 factorial. This is tough. This whole thing has a 1 over a 1 times a 1. Yeah, that one we didn't need to worry about. That's just a 1. But the rest of them we do need to worry about, and look for the cool cancellations that happen in this. That 7 factorial and that 7 factorial knock each other out. There's the 3 factorial and the 3 factorial. What's left is what I showed you before when we figured out the multinomial coefficients were directly. We got 11 factorial in the numerator. It's the only thing that survived in the numerator. And then 4 factorial, 2 factorial, and I guess 1 factorial, one of those ones. Don't really need them, do we? We only need them to make the sum of the numbers in the bottom equal to 11, which is a nice check on things. I want to have us sort of back up a little bit and kind of see the broad picture of what we've been doing. We're accumulating some ways of counting things, selections from a set, with certain restrictions. So these are going to be, the general setup is we're looking for formulas where we're picking k things from a set of size n. And one of the issues we've dealt with is whether we were worried whether the order of things mattered or not. If it doesn't matter, we'd get one formula. If it does, we'd get another. The other thing that we've seen a few examples of is repetition allowed in these things, or are we forced to have no repetition? Let's do order matters and both repetition okay and no repetition first. Both of these are easy to get to with the multiplication principle. In fact, the first one is the easiest one, because if you're allowed to repeat the symbols, well, you've got n choices for the first symbol and n choices for the second symbol, and n and n and n. It's n of them, but n times itself a bunch of times, and there are k things that we're selecting. So this one is just n raised to the k power. That's easy. This one, where we're not allowed to repeat, that's a permutation, right? We'll have n choices for the first number, then n minus 1 choices, and then n minus 2 choices, etc. And it turns out it's the p of n and k numbers we've been dealing with. The way that, if you expand it, it's n times n minus 1, etc., down to, what was that, n minus k plus 1. And that led to the easy formula that it's n factorial divided by n minus k factorial. But we'll just call it p of nk. Cool. Now, what if there's no repeats and order doesn't matter? Now, that's the kind of thing that's counted by the choice functions, c of nk, or if you would like it as the binomial coefficient version, and choose k. And yeah, that's got its nice formula too. It's n factorial divided by n minus k factorial, but also by k factorial. I think I normally write them in this order though. K factorial first, and then n minus k factorial. Of course, the order that you write them in down there doesn't matter. You can commute. Right? So, great. But what do we do here? We haven't really seen an example of this setting before. Repetition is allowed, like the letters of Mississippi, right? You may have multiple things that are multiple copies of a single symbol, but then order doesn't matter. So what would you do with something like Mississippi if you didn't care about the order? Remember the little Zen thing I was talking about with unordered collections here? If order is unimportant, then put it in the order you like. You know, if I'm talking about the letters of Mississippi, I would put them in alphabetical order. That seems strange to take a word and sort its letters so that, you know, the earliest alphabet letters come first and then the next letters. Right? I'm gonna come back and actually come to a formula here, but if we were doing Mississippi, I'd have a bunch of I's up front, 4 of them, then the M. P comes with 4 S, doesn't it? Then the 2 P's, and then the 4 S's. That's what I would convert Mississippi into if order didn't matter. I would sort it so the letters came in the order that I like. And this is a sort of thing that we can actually count. So let me do that. So as an example of the sort of thing we're just discussing, I'm going to look at some ternary numbers. Ternary means base 3, so this is, the digits are 0, 1, and 2. And I'm going to make 4 tuples, but unordered. So I'll choose the order. There'll be things like, well, I'll have them go in ascending order, because that's one I like. So 0, 1, 1, 2 would be one of these. Actually, 0, 0, 0, 0 would be one of these. That's sort of, the point is that you're allowed to have repeats, right? So, did I say that up here? Unordered, well, let's add that to the list, so it's just to make sure we're all clear about what we're talking about. Unordered, repeats, okay. So we've got 4 copies of 0, that's fine, but it's sort of, well, I guess I wouldn't say it's increasing, but it's not going down, it's what's called as non-decreasing. I might have, no zeros, I might have a couple of 1s and then a couple of 2s, etc. There's lots of options for this. So how do I actually count a thing like this? Well, I use what some people call this stars and bars. I like blanks and commas. Okay, so I'm going to show you arrangements of blanks and commas that correspond to these things. This first one I did, 0, 1, 1, 2, would consist of a blank, then a comma, then 2 blanks, then a comma, and a single blank. Right, and if you were presented with that array of blanks and commas, follow this convention. The commas come between groups of things that are the same. So any zeros that come up front would go into the blank there, and fill that in. Then the next thing after the comma would be the 1s. And I'd have a couple of 1s, and then this comma separates the 1s from the 2s, so there'd be a 2 there. See how if you have an arrangement of blanks and commas, you could fill it out to look like that. And similarly, if you have one of these numbers, you can figure out what arrangements of blanks and commas to write down. Like 4 zeros is particularly easy. That's 0, blank, 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 and then how many commas? We need commas between the zeros, the 1s, and between the 1s and the 2s. So 2 commas in every one of these things. That's the arrangement we've got here. What does this one look like? It's got no zeros, so there's no blanks before the first comma. Then there's a couple of blanks for the 1s. Then there's the second comma, and then a couple of blanks for where the 2s go. Let's challenge you to go the other direction. Suppose I have blank, comma, blank, comma, blank, blank. What number does that correspond to? What ternary 4 tuple are we looking at with the sorted ternary 4 tuples? So we know we're talking about an unordered situation. Yeah, that's 0, 1, 2, 2. Okay. Well, that would only be of use to us if we could figure out how many arrangements there are of blanks and commas. And we can. Because we know how many blanks there will be. There'll be 4. And we know how many commas there will be. There'll be commas between any zeros and any 1s, and commas between any 1s and any 2s. And so there'll be 2 commas. And that comes because we're talking about ternary. There's 3 symbols. It takes 2 commas to separate 3 symbols. Right, so how many arrangements of 4 blanks with 2 commas are there? That's not so bad. All told, there's 6 symbols. Right? And I just choose where I put, say, the commas. I could have written 6, choose 4, which would be 6 symbols, choose where to put the blanks. But those are the same. Once I choose where the commas are, everything else is the blank. If you want to, that's in a sense why the multinomial coefficient version of these binomial coefficients would be kind of a nice way to think about it. It's 6 symbols, put the 2 commas in some of those places and the 4 blanks in some other of those places. If we were doing this in general, let's mention the general case then. The general case would be unordered selections with repetition allowed of k things out of n. Excuse me. All right. So, how many blanks are we going to need? K of them. That's the K things. There I go again. Sorry. K blanks. What about commas? How many commas are we going to need? Well, we're talking about an n set. So n was 3 in my last example. We need enough commas to separate n things, or n groups of things, some of which may be empty. Well, that's n minus 1. The total number of symbols is n plus k minus 1, and we will either choose k of them or n minus 1 of them, depending on your preference. So, yeah, here's the formula. It's n plus k minus 1. I usually just rearrange things so it looks like that. Choose k. Or if you prefer, n minus 1 could go there too. So that's the formula to go back and fill into that last position in the big table that was up here in the upper right. N plus k minus 1, choose k.